This is just a brief video introduction to the idea of slope fields, which is a kind of a way to think of the solution to, or a graphical representation of the solution to a differential equation. So this is going to be just a very brief overview about what a slope field is and how we generate a slope field. So let's look at this first differential equation here. I have the derivative of a function is equal to x plus the function. All right, and what we want to do is think about graphically what is the derivative. All right, we know the slope of the tangent line at a particular point, but that's what the derivative is. Right, so if we want to find the derivative at a point, say x equals 2, that will give us the slope of the tangent line to the function at x equals 2. And in general, you know, if I have, for example, the derivative equals x squared, it means that if you tell me what the value of x is, I'll tell you what the slope of the tangent line is at any value of x by just squaring the value of x. That would give that to me. So that's the important thing here, is that we need to think about this in terms of the slope of a tangent line. And this is going to be basically a formula to help us figure out what the slope of the tangent line is at a particular point. So for example, at the point 0, 0, I would put in 0 for x, 0 for y. The slope of the tangent line is going to be 0. So it's going to change. So I don't want to just draw a horizontal line across. But I know at 0, 0 it's flat. Right? What about at 0, 1? Well, at 0, 1 the slope is going to be 1. So that's going to look something like this. And at 0, 2 the slope will be 2, because 0 plus 2 is 2. So it gets a little bit steeper and a little bit steeper and a little bit steeper and steeper, and so on. All right. Likewise, coming down here at 0, negative 1, it's going to be negative 1, then negative 2, negative 3, negative 4, negative 5. All right. So let's just continue in that way, looking at, and we'll try to just at least generate this much of a slope field. So here I have the point 1, 0, so I know that the slope is 1. At 1, 1, the slope is 2. And then at 1, 2, it's 3, 4, 5, 6. They're becoming more and more steep. Likewise down here at 1, negative 1, it's going to be 0, right? And then, so you can kind of basically think of this whole thing being shifted down, right? This was 1, that's 1. This was 2, that's 2. This was 3, that's 3. Here's the 0, there's the 0. So here at 1, negative 2, then I'll be at negative 1, and then negative 2, negative 3, negative 4. All right. Now here at 0, 2, I'm at slope of 2. And then at 2, 1, I'm at 3, 4, and so on. They're getting more and more vertical as the slope increases. So again, 2, negative 1, my slope is going to be 1. All right. So notice I have 1 here, 1 here, 1 here. 0, 0, this will be 0 here, right? This will be negative 1, this will be negative 2, negative 3, and so on. Let's just do a couple on the other side. So here I have negative 1, 0, so my slope is negative 1. Then at negative 1, 1, it's 0. And at negative 1, 2, it's 1. And then again, increasing by 1 each time, getting more and more steep. So here I'm going to be at what, negative 2, negative 3. And again, you can see I'm just estimating, right? I'm just trying to make it a little bit more vertical each time to account for the larger slope, right? Let's just do one more here, because this gets old doing it as well as watching it. All right, so negative 2, 0, so I'm going to have a slope of negative 2, then I'm going to have a slope of negative 1, then I'll have a slope of 0, then positive 1, positive 2, positive 3. Likewise down here, this will be negative 3, negative 4, negative 5, negative 6, and so on. All right, so we can kind of see. I'll just give you an idea of what a finished one. We're going to come back to this, but this is what, you know, a more complete one might look like. It takes a while to do it by hand. They're generally done using computers, but I think there is some value to doing it by hand at least a couple times, so you can kind of see what each of these little dashes means. So let's just do a little bit of this one to kind of see the same idea. So the one thing to notice here is that for y over x squared, anytime x equals 0, this is going to be undefined, right? Because I can't divide by. So I'm not going to have anything along the y-axis. Along the x-axis, though, y is 0, so I'm just going to be 0, 0, 0, 0. Because no matter what x is, if I divide 0 by that number, then so that's going to always be 0. Let's look at along here. So this is along where x equals 1, right? So now I'm always going to be dividing by 1 squared. So really this is just going to come down to the value of y. So I'm going to have 1, and then 2, 3, 4, 5, -1, -2, -3, -4, -5. If I come out to 2, now I'm dividing by 4. So these are going to grow more slowly, right? Because now I'll have 1/4, which is pretty close to flat, right? And then 2/4, which is 1/2, and then 3/4, and then 4/4, which is 1. You know, so this is going to grow much more slowly, and then likewise down here it's going to be negative, but the same thing, right? So -1/4, -1/2, -3/4, -1, and so on. If we look on this side now, it's going to be symmetric, and the reason is these negative x values, when I square them, it's going to give me the exact same thing. The y values are the same on both sides, and the x values, because they're squared, are also the same. So this will look just like this. It'll be 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. Out here it's going to grow more slowly again. It'll be 1/4, 2/4, 3/4, and so on. So, you know, 1/4, 2/4, 3/4, 1, 5/4, and so on, and then negative down here. So kind of flat, less flat, a little less flat, or -1, -5/4, and so on. All right, so that's just to give you an idea of what these little marks mean and how they relate to, like, so we're using the dy dx, that's going to be the slope at a particular point. So we just put in a little dash to indicate that slope. And again, I'm just kind of sketching these. I'm not worrying about it too terribly much in terms of being precise. It's more just to kind of get a general idea. I want to come back to this one now and just look at, maybe I'll zoom in a little bit here. So what we want to do, there's a lot we could do, but all I'm going to do for each of these is look at this relationship between a general solution and a particular solution. So maybe I wasn't explicit before, but to be clear, these slope fields are basically the graph of a general solution, right? Because no matter where we go, these are all solution curves. So there's an infinite number of solution curves that we could draw through here that would be basically consistent with these slopes at these particular points. Remember, we said that a particular solution is one that passes through a particular point. So what I'm going to do with each of these is just draw the particular solution that goes through the point that's already given on the graph. And in order for the solution to be a particular solution, it has to be consistent with the general solution. In other words, as I go forward here, I want to stay parallel to these, right? Because I basically want to draw a curve where this would be the tangent line to the curve. And so for it to be tangent, it has to be kind of going the same direction, right? So I would want something that kind of looks like that, so that if I drew in a tangent line at that point, it would be tangent to the curve. And then I'm just going to extend that, maybe something like this. Well, I want to try to stay more parallel here, right? And then this kind of looks something like that. So this is kind of straight, right? It curves up a little bit, but this is not it's a good one to start one. It's pretty straightforward because I just want to stay parallel to these little dashes that it gets close to. Let's take a look at this one now. Clearly, these are going this way, so I want to go this way. One way to think about the idea here is you want to kind of go with the flow, right? So, in order to be consistent with the flow, and I don't have to pass through these points, but I should notice what's going on here. These, if you look, are getting more and more steep, right? They're getting more and more vertical as we go upward. So this should also get more and more vertical as we go upward. And then along y-axis, they seem to be kind of flattening out a little bit. So maybe something like this for that one. All right, how about this? Here, this one's a little bit trickier because the ones up here go away from what's in the middle here, and the ones from here also go away, but in opposite directions. So how do we decide which direction to go? I think one way to think about it is these ones are slanted downward more. If you think of this as like a current, the current is stronger here because these are flatter, right? So it looks like it's going to go down this way, right? And again, trying to stay parallel to these little dashes. And notice I have the same thing here as up here, except now they're both going in to this space between 1 and 2 on the y-axis. Here they were both going out, right? So this is going to kind of come in between here, right? It's not going to go against the grain here, right? It's going to try to stay consistent. So this all kind of seems to be flowing into this general kind of horizontal line between 1 and 2. All right, finally, let's take a look at this one. This one's a little bit more interesting because of the movement we see here. So to be consistent with this curve or this little dash here, I want to kind of stay this, but I have this one to negotiate too, so it must turn and kind of maybe come back down, you know, something like this, and then coming back this way, it just stay parallel to what's around it is basically the idea. So again, just this whole thing, the slope field is a graph of the general solution, and then by picking a particular point in the slope field and drawing a curve that is consistent with the slope field, that goes with the flow of the slope field, we can find a particular solution. And we could do that for any point. I could start here and try to draw something that, you know, that goes with this flow. Over here I could start here, I could start here. Anywhere I start, then I could go with the flow of the slope field and find a particular solution to the differential equation. So that's just a brief introduction to the slope field as a graphical representation to the solution of a differential equation.